Power Quality Engineering Services (PQES) is a recommended power quality engineering firm. Chris Bowers, a professional engineer, is the contact. Their website is / and the email address is. The phone number is 415 364.7211. PQES has experience conducting power quality surveys and EMF studies in commercial buildings, including historic buildings. They are also familiar with the unique challenges of downtown San Francisco's electrical infrastructure. Here are some examples of power quality issues and resolutions. One issue is excessive harmonics and voltage fluctuations in a high-rise office building. The impact was computer crashes, data corruption, and equipment failures. The resolution was installation of active harmonic filters and voltage regulators. Another issue is EMF exposure concerns in a medical office suite. The impact was headaches, fatigue, and other health symptoms in staff and patients. The resolution was conduct of an EMF survey and implementation of shielding measures to reduce EMF levels. Another issue is grounding problems in an industrial facility. The impact was electrical shocks, equipment damage, and production interruptions. The resolution was upgrade of the grounding system and installation of lightning protection. When selecting a power quality consultant, look for someone who is experienced in commercial buildings and has a strong understanding of electrical theory. Be prepared to provide the consultant with detailed information about the building's electrical system and the specific issues you are experiencing. The cost of a power quality survey can vary depending on the size and complexity of the building. However, it is a valuable investment that can help you identify and mitigate power quality problems, improve equipment reliability, and ensure a safe and productive work environment. Power quality refers to maintaining a steady state sine wave of voltage and current at the proper magnitude, frequency, and phase. Any deviation from this ideal is considered a power quality problem. Harmonics are distortions of the voltage or current waveform caused by nonlinear loads. Nonlinear loads draw current in abrupt pulses, which creates harmonic frequencies that are multiples of the fundamental frequency, typically 60 Hz. These harmonics can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with communication systems. Voltage fluctuations are variations in the voltage level. These fluctuations can be caused by a variety of factors, including changes in the load in the system, faults in the system, and switching operations. Voltage fluctuations can cause equipment to malfunction or fail. Grounding problems occur when the grounding system is not properly installed or maintained. A proper grounding system provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and damage. Grounding problems can cause a variety of problems, including electrical shocks, equipment damage, and interference with communication systems. EMF stands for electromagnetic field. EMF are created by electrical currents. There are two types of EMF: electric fields and magnetic fields. Electric fields are created by voltage and magnetic fields are created by current. EMF can be found everywhere, from power lines to household appliances. Some people are concerned about the potential health effects of EMF exposure. There is no conclusive evidence that EMF exposure causes any health problems, but some studies have suggested a possible link between EMF exposure and certain types of cancer. If you are concerned about EMF exposure, you can take steps to reduce your exposure, such as avoiding prolonged exposure to EMF sources and using shielding materials. When evaluating power quality, several factors should be considered. Firstly, harmonic distortion, which measures the amount of harmonic content in the voltage or current waveform. Secondly, voltage fluctuations, which measures the variations in the voltage level. Thirdly, grounding impedance, which measures the impedance of the grounding system. Fourthly, transient voltages, which are short-duration high-voltage spikes. And fifthly, power factor, which measures the efficiency of electrical power usage. Mitigation techniques for power quality problems include the installation of harmonic filters, which are devices that reduce the amount of harmonic content in the voltage or current waveform, the installation of voltage regulators, which are devices that maintain a constant voltage level, the upgrade of the grounding system, which improves the grounding system, and the installation of surge suppressors, which are devices that protect equipment from transient voltages. A power quality survey is a comprehensive assessment of the electrical system that identifies potential power quality problems. The survey typically includes measurements of voltage, current, harmonics, grounding impedance, and transient voltages. The results of the survey can be used to develop a plan to mitigate any power quality problems that are identified. An EMF study is an assessment of the electromagnetic fields in a given area. The study typically includes measurements of electric and magnetic fields. The results of the study can be used to determine if there are any areas where EMF levels are above the recommended limit. Shielding measures can be used to reduce EMF levels. Shielding materials can be used to block or absorb EMF. Shielding measures can be used to protect people and equipment from EMF exposure. Power quality is a critical aspect of modern electrical systems. Power quality problems can cause a variety of problems, including equipment failure, data loss, and safety hazards. By understanding the causes and effects of power quality problems, you can take steps to mitigate these problems and ensure a safe and reliable electrical system. Harmonic filters are designed to reduce harmonic distortion in electrical systems. Harmonics are unwanted high-frequency components in the voltage or current waveform that can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with communication systems. Active harmonic filters use electronic components to actively cancel out harmonic currents, while passive harmonic filters use inductors and capacitors to filter out harmonic currents. Voltage regulators are designed to maintain a constant voltage level in electrical systems. Voltage fluctuations can cause equipment to malfunction or fail. Voltage regulators use electronic components to automatically adjust the voltage level to compensate for variations in the input voltage. Grounding systems are designed to provide a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and damage. Grounding systems should be properly installed and maintained to ensure that they are effective. Surge suppressors are designed to protect equipment from transient voltages, which are short-duration, high-voltage spikes. Transient voltages can be caused by lightning strikes, switching operations, and other events. Surge suppressors use electronic components to clamp the voltage level to a safe level, which protects equipment from damage. Power factor correction is a technique used to improve the efficiency of electrical power usage. Power factor is a measure of the relationship between voltage and current in an electrical circuit. A low power factor indicates that the electrical system is not using power efficiently. Power factor correction can be achieved by installing capacitors or inductors in the electrical system. Regular power quality monitoring can help to identify potential problems before they cause equipment failure or data loss. Power quality monitoring equipment can be used to measure voltage, current, harmonics, grounding impedance, and transient voltages. The data collected from power quality monitoring can be used to track trends and identify potential problems. Power quality analysis software can be used to analyze power quality data and identify potential problems. Power quality analysis software can also be used to simulate the effects of different power quality mitigation techniques. Implementing a power quality management program can help to ensure a safe and reliable electrical system. A power quality management program should include regular power quality monitoring, power quality analysis, and the implementation of power quality mitigation techniques. It is important to consider the specific needs of the application when selecting power quality equipment. Different types of equipment are designed for different applications. For example, some equipment is designed for use in industrial facilities, while other equipment is designed for use in commercial buildings. Understanding electrical theory is essential for solving power quality problems. Electrical theory provides the foundation for understanding how electrical systems work and how power quality problems can occur. Consulting with a qualified power quality engineer can help to identify and mitigate power quality problems. A qualified power quality engineer has the knowledge and experience to assess the electrical system and recommend appropriate solutions. Power quality standards provide guidelines for acceptable levels of power quality. Power quality standards can be used to assess the performance of electrical systems and to ensure that they meet the required levels of power quality. The Institute of Electrical and Electronics Engineers, or IEE, is a professional organization that develops standards for electrical engineering. The IEE standards for power quality are widely used in the industry. The National Electrical Code, or NEC, is a set of standards for the safe installation of electrical wiring and equipment. The NEC contains requirements for grounding, bonding, and overcurrent protection, which are all important for power quality. Understanding the specific requirements of the NEC is essential for ensuring a safe and reliable electrical system. The cost of power quality equipment and services can vary depending on the complexity of the problem and the type of equipment or services required. However, the cost of addressing power quality problems is often less than the cost of equipment failure, data loss, and safety hazard. Investing in power quality can provide a significant return on investment. Power quality solutions can improve equipment reliability, reduce downtime, and improve safety. By addressing power quality problems, you can ensure a safe and reliable electrical system for your facility. Different types of loads can have different impacts on power quality. Linear loads, such as incandescent light bulbs and resistive heaters, draw current in a sinusoidal waveform which does not create harmonics. Non-linear loads, such as computers, electronic ballasts, and variable frequency drives, draw current in abrupt pulses, which creates harmonics. It is important to understand the types of loads in your facility and how they can impact power quality. The location of equipment can also impact power quality. Equipment that is located close to nonlinear loads may be more susceptible to harmonics. Equipment that is located far from the power source may be more susceptible to voltage drops. It is important to consider the location of equipment when evaluating power quality. The age of the electrical system can also impact power quality. Older electrical systems may have outdated wiring and equipment, which can make them more susceptible to power quality problems. It is important to have your electrical system inspected regularly to identify potential problems. Proper grounding and bonding are essential for power quality. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. Bonding connects all of the metal parts of the electrical system together, which helps to prevent voltage differences between different parts of the system. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect equipment from overloads and short circuits. Overcurrent protection devices should be properly sized and installed to ensure that they provide adequate protection. Surge protection devices are designed to protect equipment from transient voltages, which are short-duration, high-voltage spikes. Surge protection devices should be installed at the service entrance and at sensitive equipment. Power conditioning equipment can be used to improve power quality. Power conditioning equipment includes voltage regulators, harmonic filters, and surge suppressors. Power conditioning equipment can be used to address a variety of power quality problems. Energy efficiency and power quality are often related. Improving energy efficiency can also improve power quality. For example, using energy-efficient lighting can reduce harmonic distortion. Power quality monitoring can be used to track energy consumption and identify opportunities for energy savings. Power quality and reliability are both important for the operation of electrical systems. Power quality refers to the quality of the voltage and current waveforms. Reliability refers to the ability of the electrical system to provide power without interruption. Power quality problems can cause equipment failure, data loss, and safety hazards. Reliability problems can cause downtime and lost productivity. Addressing both power quality and reliability is essential for ensuring a safe and efficient electrical system. Power quality disturbances can be classified into several categories, including transients, short-duration variations, long-duration variations, voltage imbalance, waveform distortion, and frequency variations. Transients are impulsive or oscillatory events in the voltage or current waveform. Short-duration variations include voltage sags, voltage swirls, and interruptions. Long-duration variations include undervoltage and overvoltage. Voltage imbalance occurs when the voltages on the three phases of a three-phase system are not equal. Waveform distortion includes harmonics, notching, and noise. Frequency variations occur when the frequency of the power system deviates from its nominal value. Each type of power quality disturbance can have different causes and effects. It is important to understand the different types of power quality disturbances in order to effectively diagnose and mitigate power quality problems. Power quality monitoring equipment can be used to measure and record power quality disturbances. Data collected from power quality monitoring can be used to identify the causes of power quality problems and to evaluate the effectiveness of power quality mitigation techniques. Advanced power quality analyzers can provide detailed information about power quality disturbances, including the magnitude, duration, and frequency content of the disturbances. This information can be used to develop targeted solutions to power quality problems. Power quality standards define acceptable levels of power quality for different types of equipment and facilities. Power quality standards can be used to assess the performance of electrical systems and to ensure that they meet the required levels of power quality. There are several different power quality standards, including IEEE 519, which defines recommended practices for harmonic control in electrical power systems, and IEC 61000, which is a series of international standards for electromagnetic compatibility. Understanding power quality standards is essential for ensuring that electrical systems are designed and operated in a way that minimizes power quality problems. Power quality mitigation techniques can be used to reduce the impact of power quality disturbances on equipment and facilities. Power quality mitigation techniques include surge suppression, voltage regulation, harmonic filtering, and power factor correction. The selection of appropriate power quality mitigation techniques depends on the specific power quality problems that are being addressed. Power quality studies can be used to identify and evaluate potential power quality problems. Power quality studies typically include a review of the electrical system design, measurements of power quality parameters, and simulations of power system performance. The results of power quality studies can be used to develop recommendations for power quality mitigation techniques. Power quality training can help to improve the knowledge and skills of electrical engineers and technicians in the area of power quality. Power quality training can cover a wide range of topics, including power quality fundamentals, power quality monitoring, power quality analysis, and power quality mitigation techniques. Properly trained personnel are essential for ensuring that electrical systems are designed, operated, and maintained in a way that minimizes power quality problems. Power quality is an ongoing process. Power quality problems can change over time as electrical systems are modified and as new equipment is added. It is important to regularly monitor power quality and to implement power quality mitigation techniques as needed. By taking a proactive approach to power quality, you can ensure that your electrical systems operate reliably and efficiently. The severity of harmonic distortion is quantified by total harmonic distortion, or THD. THD is a percentage that represents the ratio of the RMS value of the harmonic content to the RMS value of the fundamental frequency. High THD can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with communication systems. The acceptable level of THD varies depending on the application. IEEE 519 recommends that THD be limited to 5% at the point of common coupling for most industrial and commercial facilities. Voltage sags and swells are short-duration variations in the voltage level. Voltage sags are a decrease in the voltage level to between 10% and 90% of the nominal voltage for a duration of 0.5 cycles to 1 minute. Voltage swells are an increase in the voltage level to between 110% and 180% of the nominal voltage for a duration of 0.5 cycles to 1 minute. Voltage sags and swells can be caused by a variety of factors, including faults in the power system, switching operations, and large motors starting. Voltage sags and swells can cause equipment to malfunction or trip. Uninterruptible power supplies, or UPS, are used to protect sensitive equipment from voltage sags, voltage swells, and interruptions. A UPS provides a backup power source that can supply power to the equipment during a power outage. UPS systems are commonly used to protect computers, servers, and other critical equipment. Transient voltage surge suppressors, or TVSS, are used to protect equipment from transient voltages. Transient voltages are short-duration, high-voltage spikes that can be caused by lightning strikes, switching operations, and other events. TVSS devices clamp the voltage level to a safe level, which protects the equipment from damage. TVSS devices should be installed at the service entrance and at sensitive equipment. Power factor correction capacitors are used to improve the power factor of electrical systems. A low power factor indicates that the electrical system is not using power efficiently. Power factor correction capacitors can be installed to increase the power factor, which reduces energy losses and improves the capacity of the electrical system. Harmonic filters are used to reduce harmonic distortion in electrical systems. Harmonic filters can be either passive or active. Passive harmonic filters use inductors and capacitors to filter out harmonic currents. Active harmonic filters use electronic components to actively cancel out harmonic currents. Active harmonic filters are more expensive than passive harmonic filters, but they are more effective at reducing harmonic distortion. Voltage regulators are used to maintain a constant voltage level in electrical systems. Voltage regulators can be either tap-changing transformers or electronic voltage regulators. Tap-changing transformers adjust the voltage level by changing the number of turns on the transformer winding. Electronic voltage regulators use electronic components to automatically adjust the voltage level. Electronic voltage regulators are more expensive than tap-changing transformers, but they provide more precise voltage regulation. Grounding is an important aspect of power quality. A properly grounded electrical system provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. Grounding also helps to reduce noise and interference in electrical systems. Bonding is the process of connecting all of the metal parts of an electrical system together to create a low impedance path for fault current. Bonding helps to prevent voltage differences between different parts of the system, which can reduce the risk of electrical shock. The National Electrical Code, or NEC, contains requirements for grounding and bonding. It is important to follow the NEC requirements to ensure a safe and properly grounded electrical system. Regular maintenance is essential for maintaining power quality. Regular maintenance should include inspections of electrical equipment, testing of grounding systems, and cleaning of electrical panels. Regular maintenance can help to identify potential power quality problems before they cause equipment failure.